Now, if we want to determine the relationship between the shear stress and the position y, do that a couple different ways. One way is we can go back before we found that the shear stress is equal to this equation right here, and we knew that C3 is equal to 0, so therefore the shear stress is equal to the change in pressure over L times y. Or we know the constitutive relationship is tau equals mu times the viscosity times the velocity gradient. Since we know Vx, all we have to do is differentiate Vx to figure out dVx over dy, which is going to end up equals to this. We can just plug this in to this velocity gradient right here to be able to figure out that the shear stress is equal to this. So a lot of times it's not going to happen to be this easy where you can go back and plug it in, and you're going to have to go this route. But in this case we have two easy ways to do it. We also want to note another boundary condition that I haven't mentioned too much, is that Vx in this case is symmetric around y equals 0. So again, if we look at y equals 0 is the center line point, and it's symmetric around, it's a parabola, so this is the maximum velocity. So dVx divided by dy is equal to 0 at y equals x. You can think of the symmetry, the maximum, it's all the same, and it's going to be able to then give you, since this is equal to 0, your shear stress is going to be equal to 0 at y equals x. So we could have also used this boundary condition to solve our equation. So again, we got our shear stress, Tyx is equal to this term we got earlier, and if we would have just at that point put in at y equals 0, shear stress is equal to 0, we would have found that C3 is equal to 0, and therefore our shear stress would have we would have found our shear stress immediately. You could have also done it with the velocities. So if you went ahead and used your constitutive relationship, you would have known that dVx dy is equal to 0, so this would have been equal to 0, and y is equal to 0, and C3 would then be equal to 0. And then we would have just had this equation to continue to differentiate, and we could have used our boundary condition. After integrating this, we could have used our boundary condition of y equals h over 2 as for our y portion, and our Vx would be equal to 0, and so then that would have probably made it the algebra a little bit faster if we would have done it that way. So you could do it either way, it's fine. But just understand the different boundary conditions you can use. So where is the velocity of maximum? We mentioned that the velocity of max, since it's a parabola, it's at y equals 0 based on our coordinate system here. And so if that's the case, we use our velocity profile, put in y equals 0, and we can figure out a term for the Vmax. So our Vmax is equal to delta P h squared divided by 8 mu L. We can just take this Vmax, plug it, this is your Vmax basically right here, as you can see, and so this is going to be your velocity profile in terms of Vmax. So the final things we can do here is figure out like the flow rates and the average velocity. So if we want to figure out the flow rate in this situation, it's just going to be the surface integral of all the velocity vectors. So here's our flow rate, and it's in the x and y direction. So the y goes from negative h over 2 to positive h over 2, and the z direction is from the width of it, 0 to w. So we have our double integral, and we're going to plug in Vx into our double integral, and we can pull out Vmax and w, since they are they're going to be constant and not dependent on y. So now all we have to do is integrate this portion. So if we integrate that, we find out that q is equal to Vmax w h minus 1/3 h, and we get this for our flow rate, 2/3 Vmax wh. So now if we want to find the average velocity, remember the average velocity is 1 divided by area times basically this is the flow rate q, as you can see from up here. It's just your velocity vectors over your surface area integrated. So if we look at this, we go ahead and do our equation again, and we see that since all of this is Q, your average velocity is Q divided by A, so therefore Q is equal to the average velocity times the width times the height for this rectangular channel. And your average velocity is then going to be equal to, all we're doing is going 1 divided by A, you put in your Q that we found earlier right here, and it's 1 over your area is your width times your height times Q. These two are going to cancel out, so your average velocity in a pressure driven flow through rectangular channels is equal to 2/3 V max.